We are diving deep into the future of mobility today, and we've got some really complex source material in front of
We
us.
do. But it also offers some startlingly clear answers in a couple of very different areas.
Right. We're tackling ground transportation through two crucial lenses. First, immediate real-world safety data from autonomous vehicles.
And second, the deep environmental analysis, the life cycle assessment.
It's this tension between them. Our mission for this deep dive is to basically synthesize this for you. We want to give you the actionable knowledge to understand if these new technologies are really safer right now and if they're truly greener across their entire life.
And those are two very different questions.
Okay, let's unpack this. Let's start with something immediate and measurable. Road safety.
The comparison we're looking at is, well, it's pretty groundbreaking, and that's because of the data source itself. We're looking at Waymo One autonomous driving service data.
Specifically, the insurance claims from their accidents.
Exactly. And that's being compared against this huge localized baseline of human drivers from Swiss Re, which is, a giant in the insurance world.
So why is using liability insurance claims better than, say, the standard police reports? I mean, that's what everyone thinks of when you talk about accident stats.
It really comes down to two things.
Yeah.
Consistency and depth. Police reports are, they're mandatory for the really bad stuff, serious injuries, fatalities.
So they're biased toward the extreme.
They are. Claims data, on the other hand, it gives you a much more complete picture because it captures just a much higher frequency of crashes that are relevant to safety.
You mean all the small stuff, the property damage, the fender benders that police never even show up for?
Exactly. I mean, if you only look at police reports, you could be missing, 80% of the statistical picture of what's really happening out there.
Wow.
And what's more, claims data gets all the injuries, even the ones with delayed symptom onset.
The ones people report weeks later.
Right. But here's the most critical part, the sort of technical advantage. It's the liability claims adjudication process.
Okay.
That whole process is built to figure out one thing. Who was at fault? Who caused it? Unlike a lot of police reports, which just document the scene, the insurance process assigns fault with real rigor.
It answers the fundamental question. Okay, so let's get to the numbers. We're talking about Waymo's most advanced mode here.
Level 4 autonomy. This is rider-only mode. No human safety driver in the car, operating in San Francisco and Phoenix.
And the mileage.
The study covered over 3.8 million miles, just in that rider-only mode.
And the findings.
The core finding for bodily injury claims is, frankly, stunning. Zero.
Zero claims.
Zero claims incurred by the Waymo driver over all those miles.
That's in busy cities like San Francisco and Phoenix. Zero. How does that compare to the human baseline?
Well, the human baseline, which was carefully calibrated for the same zip codes and mileage, it clocked 1.11 bodily injury claims per million miles.
So for a human, that's like one claim every 900,000 miles or so, which is a long way.
It's a huge distance, but the autonomous system just eliminated it.
Right.
Completely, at least in this data set.
A 100% reduction. That isn't a projection. That's just hard data over millions of miles. What about property damage?
Also drastically reduced.
Yeah.
The human baseline was 3.26 property damage claims per million miles. The Waymo driver, 0.78.
That's a 76% reduction.
It is. And even in their testing mode, with a human specialist monitoring, bodily injury claims were still down by 92%. Just powerful evidence of the system's ability to mitigate risk.
Okay, I have to play devil's advocate here. The biggest critique of these studies, you said the baseline was calibrated, but Waymo's cars mostly stay off high-speed freeways.
Right, their operational design domain, yeah.
But the human baseline includes freeway driving, which is statistically safer per mile.
Yeah.
Aren't you just making the human drivers look worse by comparison?
That's a fair challenge, a necessary one. And the study authors, they looked at this directly. And while it's true, freeways tend to be lower frequency but higher severity. The human baseline they used was pulled from the frequency seen for local residents right there.
Within those specific zip codes.
Exactly. And given how insurance pricing works, they use that local frequency as the best proxy. The authors concluded that the impact of the freeway difference is expected to be immaterial to the final estimate. It's still a good comparison.
So if you want the real picture of road safety, you follow the insurance liability, not just the police report. And right now, these systems are showing huge, demonstrable safety gains.
That's the story the data tells.
That is a very encouraging short-term win. But now we have to pivot. We have to turn to the multi-decade challenge, sustainability.
Right. We're moving from immediate physical safety to long-term planetary health.
And that means we have to look beyond the tailpipe. We need to adopt a cradle-to-grave perspective.
Absolutely. This is where the life cycle assessment, or LCA, becomes just an essential tool. You can think of an LCA as the ultimate environmental audit.
So it's a method to estimate all the material, all the energy flows, and analyze the environmental effects over the entire life of a car.
The entire life, from, mining the raw materials to manufacturing, distribution, the actual driving phase, and then all the way through to recycling and disposal.
We have to do that because the last thing you want is to just shift the environmental burden around.
Exactly. You can't celebrate clean exhaust if you've just moved all the pollution upstream to a mine or a factory. We need a holistic view.
So what are the actual units we're measuring here? How do you quantify this huge environmental footprint?
We use two main metrics. The first is global warming potential. It's expressed as greenhouse gas emissions, or GHG.
Measured in grams of CO2 equivalents per kilometer.
Right, CO2 EQ kilometer. And the key is that equivalence part. It's not just carbon dioxide. It lumps in methane and nitrogen monoxide.
And those have some pretty big multipliers.
They really do. We use these standardized warming potential factors. So 1 kilogram of methane, for instance, is equivalent to 34 kilograms of CO2. But nitrogen monoxide, N2O, that's the real monster. 1 kilogram of N2O is equivalent to a massive 298 kilograms of CO2.
Almost 300 times more powerful. That's staggering. It tells you that even a tiny amount of N2O has to be accounted for.
Absolutely. And the second unit we track is the cumulated primary energy consumption. Basically, kilowatt hours total per kilometer.
And you break that down by source.
You have to. How much came from fossil fuels versus how much came from renewables? Because low emissions from burning a lot of fossil fuels isn't really a win.
Okay, let's get into one of the most contentious areas here, biofuels and land use change. The classic argument is that if I burn ethanol, it's carbon neutral because the plant just absorbed that CO2.
That's the starting assumption, yes. The biogenic CO2 from combustion is counted as zero as long as the biomass was, grown sustainably. But the real environmental cost often hides in the land use change, or LUC.
And you have to explain the difference between direct and indirect LUC, because that's where all the controversy seems to be.
Right. So direct LUC, DLUC, is straightforward. A farmer converts a pasture into a field to grow corn for ethanol. That's a direct change.
Simple enough.
Indirect LUC, ILUC, that's the really complex global piece of the puzzle.
How does that work globally?
Okay, imagine a huge amount of cropland in the U.S. that was growing animal feed is suddenly switched over to growing biofuels instead.
Okay.
Well, the demand for animal feed didn't disappear. It just got displaced. So that pushes feed production somewhere else on the planet, which could lead to, say, a rainforest in Brazil being cleared to make new farmland.
So the demand for a green fuel in one country ends up causing deforestation halfway across the world.
Exactly. And the GHG emissions from that conversion, releasing all that carbon stored in the soil and trees, can be immense. I mean, some models show extreme examples. Fame from palm oil could generate up to 231 grams of CO2 equivalent per megajoule.
And palm oil is notorious for that because of how it drives expansion into sensitive habitats.
Precisely. It can create a totally perverse environmental outcome. Now, to be fair, in the formal LCA results, it's typically only DLUC that's formally included.
Why is that?
Because ILUC relies on these really complex economic models, not direct measurement, so its inclusion in official carbon budgets is pretty debatable.
Let's transition to what's becoming the main event in this debate, manufacturing.
Yes.
Here's where it gets really interesting. If we're talking about battery electric vehicles, BEVs, everyone focuses on the clean operation, zero tailpipe emissions. But what about the massive carbon cost to build the battery in the first place?
For BEVs, the manufacturing phase is, without a doubt, a huge front-loaded part of its life cycle emissions. Based on some broad estimates, the average emissions for making an automotive battery system is about 171 kilograms of CO2 equivalent for every kilowatt hour of capacity.
That's a lot of embedded carbon before the car even rolls off the line. It's kind of humbling to think that my EV's impact depends less on how I drive and more on whether the factory was powered by coal or hydro.
It absolutely shifts the burden, but there is some hope on the back end of the cycle.
Okay.
That 171 kilogram figure, it drops a lot, down to 95 kilograms. If that battery gets a crucial second life as stationary energy storage before it's finally recycled.
So the end-of-life plan makes a huge difference to the total footprint.
A profound difference. That second life battery ecosystem is almost as important as the battery tech itself.
What else influences that total GHG number for a BE?
Well, the single biggest variable is the country-specific electricity mix used for manufacturing. I mean, it's pretty simple. A battery made in a place like China, with a lot of coal, has a much higher footprint than one made in Norway, with tons of hydropower.
So if the world goes electric, we have to clean up the factory grid just as fast as the road grid.
Or even faster.
Yeah.
Another factor is just battery longevity. A battery that lasts 300,000 miles instead of 150,000, you're effectively cutting the manufacturing emissions per kilometer in half. Lifetime is key.
So we've covered the current state, but these studies also look ahead. What are the predictions for, say, 2030 or 2050?
The estimates are mostly based on scaling current trends. So on the vehicle side, they project ongoing efficiency gains. Think lighter materials, better powertrains, maybe a 10% drop in driving energy demand by 2030 and another 20% by 2050.
That's a huge drop in the energy you need just to move the car.
It is. And on the energy source side, the main assumption is just an ever-increasing share of renewables on the grid.
Any new technologies on the horizon?
Oh, yeah. They're anticipating broad commercialization of things like hydrogen fuel cell vehicles running on green hydrogen, also advanced biofuels from things like wood and straw, and a technology called e-fuels,
Which
synthetic fuels made using renewable electricity and a captured carbon source.
this whole progression, it's all about a constant search for more efficiency. And speaking of that, let's just briefly look at the absolute extreme end of that spectrum.
You're talking about teams like Terra TU Graz.
Exactly. These student teams aren't solving for the mass market. They're competing in things like the Shell Eco Marathon, where the only goal is to use the least amount of energy possible.
And the numbers they hit are they're absurd. Their vehicle, the Fennec, set a world record back in 2014. It achieved 1,092 kilometers per kilowatt hour.
Let's put that in terms people can understand.
Okay, so that's roughly equivalent to 9,707 kilometers per liter of gasoline.
Which is over 22,000 miles per gallon.
Yeah, it's just an exercise in eliminating every single gram of waste.
Right.
Using these hyper-specialized carbon monocoque chassis, it's what's physically possible.
It's the benchmark. But before we wrap up, I need to circle back to where we started. Autonomous vehicles.
Okay.
Are autonomous systems and all the infrastructure they need, are they factored into those long-term LCA forecasts for 2030 and 2050?
That is a critical question, and the answer is no.
Really?
The studies we're drawing from, they specifically state that autonomous driving vehicles are explicitly excluded from these future estimations. They're treated as this big, unknown variable.
So what does this all mean? We've gone from zero bodily injury claims in AVs to the embedded carbon in batteries.
I think we've established that the verifiable short-term safety gains from advanced level 4 autonomy are, well, they're massive. It's an immediate societal benefit. Zero injuries over millions of miles is a bar that human drivers just can't match right now.
But that immediate win is contrasted so sharply with this complex long-term environmental challenge. The path to truly green mobility means mastering the life cycle assessment. You can't just assume electric is clean.
Not at all. You have to account for that hefty upfront cost of manufacturing. The path to sustainability really hinges on two things happening at once.
Which are?
Continuous improvements in vehicle efficiency, getting a little closer to that Fennec ideal,
Yeah.
and most critically, rapidly decarbonizing the electricity grid for production and for operation. If the factory is clean, the car is clean.
Which brings us to our final provocative thought for you to think about. We know autonomous vehicles can slash crash frequency. It's maybe the biggest safety leap in history. But if the world transitions to mass-scale electric, autonomous fleets, which means making millions of new complex batteries, how absolutely essential is it that the manufacturing grid hits 100% decarbonization immediately? I mean, does the urgent need for that safety improvement outweigh the environmental debt we'd rack up by building all those vehicles on a still dirty industrial grid?